K arms that I can pull. And imagine further, this is not how casinos really work, but imagine that each one secretly has a probability, its own individual probability. So this could go from 0 to 1. A probability of paying off. So imagine that the way these ones work is you put your coin in, and you pull the arm, and with this probability, you get back 2 coins. Or simpler even is you don't have to put coins in at all. You pull the arm, and with this probability, you get 1 coin back or nothing. OK. So each of these machines has an independent probability. The probabilities aren't related to each other, and they're not known to you. If they were known to you, what would you do? You would pick the one with the biggest P, right, over and over and over again. That would be the best thing. OK. So, and pigeons, it turns out, if you give pigeons a problem like this, actual physical pigeons, they tend to pick these things in a ratio that's related to the ratios of these probabilities. But we're smarter than pigeons, so we should always try, if we could, we would pick the best one all the time. OK, so now the question is, imagine that I say, welcome to the reinforcement learning casino. This is a very simple one, just like this. There's K arms, and you get to play 100 times for free. You get to pull 100 times an arm for free. I don't care which one. The question is, and you don't know the P's. You don't know anything except just that there's these K machines. How would you approach this problem? I'm assuming that you would like to maximize the number of coins that come out. You don't have to put any in. You just think about it for a minute. It's kind of fun to think about. OK, somebody have a strategy? What would you do in this casino? Like, this is a practical problem here. You could face it. No? No suggestions? Yes? Good, OK. So that was a great suggestion. So the suggestion is, I take some fraction of this 100, and I allocate them uniformly across these guys, right? So maybe if I have 3 arms, I spend 10 trials on each arm, estimate the probability from those results, and then pick the one that seemed to be the winner for the rest of the time. So that's actually a pretty good strategy. The optimal strategies have a character that's like that. And there's an interesting question of how many, it's a math problem. You can figure out kind of like how many of your trials should you allocate to trying to figure out what's going on. It's more complicated if we take the discounted view and we say, oh, here, come into my casino. You can play for as long as you like, but in fact, on every step, I'm going to roll a die and then throw you out, right? So that would be like the discount factor sort of view. In that case, it's a little trickier to know how much time you should spend testing things. And in fact, you should interleave testing with exploiting. So fundamentally, though, the idea is that you have to do some amount of exploration so that you can understand what your options are, and some amount of exploitation so that you can take advantage of what you've learned in the world. OK, so the problems that we face in a real, OK, so this is not an MDP in an interesting sense, right? Because there's like only one, you can see this as something like an MDP with one state and K actions. But nothing, when you pull the arm, you get some information about the reward function, really. But you don't really get to, nothing changes, right? So sometimes I like to think of an MDP casino, which has a bunch of rooms, one corresponding to each state. In each room is a bunch of bandits. And what you can do is you can pick one of these, pull the arm, get a reward or not, and then you're teleported, according to some distribution, to a different room in the MDP casino. And then you do that again. So the teleportation distribution would be the transition model. Whether you get the one out or not would be the reward. It's probabilistic in this case, but not too different. OK, so that's kind of like the problem that gets faced by my robot or by Google when they're doing ad placement, right? They show you an ad that's like taking an action. Then you might or might not click on it or do something with it. That's kind of like a reward. You could even think of states in terms of like what pages you go to next and so on. Okay, so we understand now that there's a problem of how you should choose actions in order to get information and how to exploit. And then the next question is, well, how should you learn? So if you're in an MDP and you're interacting with it, you get experience that sort of looks like this. You can think of a useful chunk of experience in an MDP as a state, an action, a reward, and a next state.